In this set of notes, we are going to quantify the conservation of work and energy. Let's go back and look at the definition of work. The definition of work in the scientific sense is force times distance. Now, there is a caveat to that. If I have an object sitting on a table and I want to drag the object, I want to do force times distance, and I want my distance to be to the right, then it is possible to exert a force up on the object that doesn't move the object at all. And in that case, I would not be doing any work because there's no distance, but I also wouldn't be doing any work if the force that I happen to exert is perpendicular or at a right angle to the distance. Another example, again, suppose I have an object sitting on a table, and suppose I pull with an angle, or pull with a force at an angle. An example of this might be pulling a child in a wagon where the handle of the wagon is at an angle. In this case, the force that I exert, while it matters, while it could pull the object, the force that I exert does not, it does some work, but it doesn't do as much work as we might think. The amount of work that it does is actually based on a component, the horizontal component. And to compute that horizontal component, I would take F times the cosine of the angle. So again, only this horizontal component would count for doing work. And then if I dragged the object a certain distance, say from here to here, then the work that I would do would be equal to this horizontal component of the force times the distance, and another way to write that would be F cosine theta times distance. So we'll come back to that in an example in a little bit. Okay, in our last assignment, we looked at different forms of energy, which are ways that work can be stored, and we understood that work and energy are interchangeable, and they are energy can be transformed into work and vice versa. So now we're going to quantify those values. We're going to start with kinetic energy. Kinetic energy is energy of motion. And an object that has kinetic energy must also have mass. So the equation for kinetic energy is 1/2 mv squared. The shorthand for it is K, or sometimes you'll see KE. And the unit for it is the Newton meter, Newton times a meter, which is also called a joule, named after James Prescott Joule. The next kind of energy that we discussed was energy due to position. And in this case, the position we're talking about is height. So an object is placed on a table, it could fall off the table. We're storing energy in that position on the table. The full name of this is gravitational potential energy. The shorthand for it is EG, which stands for E gravitational. But it's a lot to write that all out, so we'll just write EG. The equation for EG is M times G, which is the force of gravity, times the height that we lift the object. And the unit, again, is the joule. Next, we have elastic potential energy. We talked about this in Unit 7.1. Elastic potential energy is energy stored while stretching a spring. And it actually could be a spring or other elastic object, like a rubber band, anything with elasticity, a rubber ball, a tennis ball. The symbol, sometimes we'll see ES for E spring. Sometimes we'll see EEL for E elastic. And the energy stored in a spring is 1/2 kx squared, where k was the spring constant and x was how far it got stretched. And joules is the unit. Finally, dissipated energy. This is energy transferred from the system to the environment. One type of dissipated energy we're going to see, and there's more than one scenario with dissipated energy, but one type we're going to see is work done by friction. So if I have a block on a table, oopsie, let me get my block. If I have a block on a table, I've got Fg and Fn. If I pull that block at a constant speed, friction always opposes motion. And acts parallel to the surface. The normal force here acts perpendicular to the surface, or at a right angle. Okay? And the formula for the force of friction is mu times the normal force. Now, on a flat surface, the normal force and the force of gravity are equal and opposite. So in this scenario, I can replace, oopsie, that's not what I meant to do. In this scenario, I can replace the normal force with Fg, which is mg. So on a flat surface, the force of friction is mu times m times g. And if that is the case, let's see, so this is E dis. The work done by friction, the work done to drag a box like this, would be equal to the force of friction times the distance. And on a flat surface, that force of friction is mu mg, and then times the distance. Again, this is just for work done by friction to drag an object. And the unit for that is also joules. All right, let's do some sample problems. A pumpkin weighing 150 newtons is carried to the top of a 5-story building. Each story is 4 meters tall. What is the pumpkin's gravitational potential energy on the 5th floor? Okay, so first of all, we've got a 5-story building. Each floor is 4 meters tall, so this is 20 meters up. Gravitational potential energy, the formula is mgh, and 150 newtons is the gravitational force, which is mg. Gravitational force is mg. So I can make a substitution. Mg is 150. So to solve this, I can just say 150 newtons times 20 meters, which is 3,000 joules. Suppose the pumpkin is dropped to the ground. What is the kinetic energy right before hitting the ground? So now the pumpkin, oh goodness, come on, pumpkin. Doesn't want to do it. Maybe the square will do it. There we go. Okay, so the pumpkin falls. So when it falls, the type of energy changes, but the amount of energy stays the same. So if it had 3,000 joules of gravitational potential energy at the top, it's going to have 3,000 joules of a different kind of energy, kinetic energy, at the bottom. So the answer here is just 3,000 joules, the same as before. What is the pumpkin's velocity right before it hits the ground? Well, now I can use the formula. I know that kinetic energy is 1/2 mv squared. The amount of kinetic energy is 3,000 joules. the mass of the pumpkin I need to determine. Fg equals mg, 150 newtons equals m times 9.81. I'll divide, and I get that m is 15.2 kilograms. And so that goes here. It's v squared. Okay, now I will solve, let's see, 3,000 divided by 15.2. 394.7. And when I square root both sides, the velocity is 19.9 meters per second. All right, let's keep it going. A car is being loaded onto a truck by pulling it up a plank inclined at 20 degrees above the ground. The plank has a length of 6 meters. And the car has a mass of 1,500 kilograms, pardon me. What is the increase in the car's gravitational energy? All right, for that we need the height, because the gravitational potential energy is mgh. So I'm going to use trigonometry. I have my marked angle, I have the opposite side, and I have the hypotenuse. And I know the sine ratio is opposite over hypotenuse. So the sine of 20 equals h over 6. Oops. So when I multiply both sides by 6, I get 2.05. And then I'll plug my values into the formula. M is 1,500 kilograms, G is 9.81, H is 2.05. And I get 3,196. I'm going to round it to 30,196. I'm going to round it to 30,200 joules. How much energy is lost to friction, heat, and sound if it takes 90,000 joules to get the car to the top of the ramp? So what we're saying here is that in a frictionless world, to get that car to the top of the ramp should only take 30,200 joules. But in actuality, it took 90,000 joules. So the dissipated energy here is going to equal the work that it took us to get it to the top of the ramp minus the energy that it actually has sitting on top of the ramp. And the energy that it has sitting on top of the ramp is the gravitational potential energy. So we would take 90,000 minus 30,200, and we get 59,800 joules is dissipated. Again, we put in 90,000 joules of work, but 59,000 is dissipated, leaving us with an object that has 30,200 joules of energy. Example 3, a 20-kilogram suitcase is raised 3 meters above a platform by a conveyor belt. Okay. So here we're not given any angles, but we do have a height and a mass. How much work is done on the suitcase? The work done on the suitcase is going to equal the gravitational potential energy that the suitcase has at the end. And here we are assuming that it's frictionless, which maybe is not a good assumption. I don't know, but we got to go with what we've got here. So that's the formula for gravitational potential energy is mgh. So I'm going to take 20 kilograms times 9.81 times 3 meters. And I get 588.6 joules. Example 4. Upon arrival to an airport, a passenger picks up her suitcase and drags it with a 100 Newton force at a 60-degree angle for 200 meters from the airport exit to her car. So in this one, I was picturing one of those suitcases that has like a handle that you can pull out. So I've got this handle that you can pull out, and the force that's being exerted, let's see if I can get this going here. There's our force of 100 newtons. That's our hypotenuse. 60 degrees. And she's going to drag this thing, how far? 200 meters. So I'm going to go back to the formula that I had from the beginning, that the work is the F cosine theta times the distance. So the work is going to be 100 times the cosine of 60 times 200 meters. And that gives me 10,000 joules of work. By the way, all that work, all it does is overcome friction, because at the end, the suitcase stops rolling immediately when you stop pulling it. Example 4, Joe tries to push his car up a hill. He pushed with a force of 300 newtons at an angle of 30 degrees, but the car won't move. Okay, our distance here is 0. So I have a force, I have an angle, but my distance is 0. And what happens when I multiply by 0? I get 0. So no work is done when an object is not moved. Last example, how much work must be done to accelerate a car of mass 1,000 kilograms from 0 meters per second to 15 meters per second? Okay, so here the work that we do is going to turn into kinetic energy. So we want to find the kinetic energy of the car at the end. So we're going to take the mass of the car is 1,000. The final velocity of the car is 15. So we get 112,500 joules. All right, thanks for listening.